we won't let you sleep, we will make you work. So this afternoon we have two components. One is lecture, theoretical component. The other one is introduction to a software. That software is a little bit intense, but at least hopefully by today you will have some familiarity, you will have gained some familiarity, and then you can go ahead and practice at your own convenience. So that's the goal. So just to quickly recollect where we left off before lunch, there's modal signature, current signature analysis. So it's like we tap the current signal to its harmonic spectrum and look for variations. So that is there. So now the question comes, how do we know which frequency to look for when there is an eccentricity fault? So that is the question we are trying to answer at this point. Okay. So how to know? Should I get a frequency here due to eccentricity, or should I not get a frequency there due to eccentricity? Something that I do not know. So we must have some kind of theoretical basis to explore what kind of frequency should I anticipate in the line current spectrum when non-uniform air gap exists. In literature, there is an approach called as MMF specific permeance analysis. So quickly recollecting.
Sir, I have one doubt. Sir, can you go back to the previous?
Yes.
Instead of asking, like in between, like we may have some peaks also, like magnitude versus frequency, like spectrum, those lines are maybe having the substance peak value. Right? So it's actually maybe the changing that whole should do by the time you are having that variation, like the three lines. Whereas one line you consider that maybe that's not required for us. But my question is that how do we know that that is not required? Maybe in between also we are having the lines.
Exactly. So that's the question. So the answer to that question is this component, right? Basically, I do not know whether this is eccentric related or
Yes.
nobody knows. So we have to carry out an analysis. And that analysis is called as MMF specific permeance analysis. Okay, so that's what we are going to do now. It's all mathematical. So the goal is to make you write, derive equations, solve equations. Okay, and hopefully that will not let you sleep. So what is MMF? MMF we know is the product of flux and reluctance. Right? So we can write mathematically many forms. What is reluctance? Reluctance is length of the gap divided by permeability times area of the gap. And we also know reluctance is the inverse of permeance. Permeance is the inverse of reluctance. Permeance is the ability of the magnetic medium to allow flux lines to pass through. Whereas reluctance is the opposite. So in order to calculate flux, we need MMF and we need to divide by reluctance, or we can multiply it with permeance. And what is flux density? Flux per unit area. So if I divide the product of MMF and permeance by unit area, I get flux density. So what I am going to say is, I am going to call this as specific permeance. And this is MMF. So the flux density in the air gap can be easily synthesized if I know the MMF and the permeance associated with the system. So using this expression, let us try to get an expression for specific permeance. So permeance is mu air gap over length of the gap. Permeance by area is specific permeance. So I cancel this out. So what am I left with in specific permeance? P by A is nothing but mu by L gap. Right? Is everybody following? What is mu? Mu is a constant. So I can say that the specific permeance depends entirely upon the inverse of my air gap length. So this is an important relationship. Depends entirely upon 1 over the gap, which is nothing but inverse of air gap length. So is everyone in agreement with what I have said? So now we will try to do this analysis. So we know that if I can somehow model my air gap and its inverse as a function, and if the MMF for a machine is easy to guess. MMF is ampere turns, right? So you know the turns, and if you know current, you can get ampere turns. It's not a big problem. So in MMF specific permeance analysis, what we will be doing is we will be looking at the MMF associated with the stator coils of a three-phase machine. This MMF, when interacting with the non-uniform distribution of air gap, will produce some flux density in the air gap. This flux density will induce currents in the stator coil itself, provided certain conditions happen. So that's the core of the problem. So the way things work is a little bit more complex than this, but the idea is you start with three-phase coil, you circulate current through it, it produces an MMF. The MMF along with the non-uniform air gap results in a permeance. So MMF times permeance per area gives flux density in the air gap. And this flux density will induce currents because it's time-changing flux density. It will induce currents in the same stator coil. And that is why we are seeing certain frequencies in the stator current. Okay. So this is the broad principle behind this MMF specific permeance analysis. So to answer the question, which frequency I should know as healthy or faulty, I should carry out MMF specific permeance analysis assuming my gap is uniform. I will get certain line frequencies. And then I will have to reanalyze assuming my gap is non-uniform. I may get same frequencies, I may get different frequencies. If I get different frequency spectrum, I know I can look for specifically 1 or 2 components in the frequency spectrum. Okay, so that's the idea. So first thing is the stator MMF. Now stator MMF in electrical engineering, we always start with a very typical assumption that the winding is sinusoidally distributed, right? But we know for a fact that it is not true. We cannot manufacture such a machine, or it becomes very intense to manufacture such a machine. So when we actually use a practical three-phase winding, stator winding, the winding distribution will result in what is known as space harmonics. How many of you have heard of space harmonics? Some of you have not. So basically, due to the spatial distribution of the three-phase windings, the waveform will not be exactly sinusoidal. So instead of having a wave like this, we may have a wave like this. Okay? Step or staircase wave. And this staircase comes because we have to place only fixed number of conductors in different slots. If I do a harmonic analysis of this waveform, I will have a fundamental component which is of interest plus higher order harmonics. That higher order harmonics are called as space harmonics. Okay? That is because of the spatial distribution of the three-phase windings. We also will have time harmonics later on when we use an inverter and inject time harmonic currents. But that is for another day. Now to capture the MMF due to the winding distribution and the space harmonics associated with it, typically we can write a mathematical expression as given on the slide. If MMF in the stator winding is given as F subscript S, we get different order of harmonics. One corresponds to the fundamental frequency, 5 and 7 corresponds to higher order frequencies in the space harmonics, and we will see that usually a 5th order, 11th order will introduce backward rotating 3-phase vector. Okay, so what do I mean by that? If I take a 3-phase system, this is phase A, this is phase B, and this is phase C. If I consider this as positive sequence, if I multiply 5 times this, 5 times, let's say this is a magnitude and an angle 0, this will be same magnitude but angle minus 120, this will be same magnitude, angle plus 120, right? If I do 5 times the angle, 5 times 0 is 0, 5 times minus 120, what is it? Minus 600. 5 times plus 120 plus 600. Okay. So in a circular frame of reference, when I have 360 degrees overall, plus 600 would be 600 is nothing but 360 plus some angle. 360 plus 240. So if I go around, this is 360 and then another 240 will be here. So you see here the phase C component, when it comes to 5th order harmonic, would be at negative 120 degrees with respect to its reference phase. Whereas phase B harmonic, when it comes to 5th order, would be at this orientation. So if you go, so minus 600 means you have to go clockwise, right? So you go 360 degree clockwise, then 360 degree 240 degree clockwise, you will end up here. Okay. So what we know for a fact is the space harmonics, certain orders would result in inverted phase sequence. So 5th order would result in inverted phase sequence. 7th order would result in same phase sequence as fundamental. 11th inverted phase sequence, 13th same, so on and so forth. This is simple mathematics. You can do and check that. So therefore, to capture the space harmonics and its impact on the phase sequence associated with the fundamental component, we have to write the MMF expression as NP5 plus or minus omega t, where n is the order of the space harmonic, p is the pole pair number. What is pole pair? If a machine has 6 poles, the pole pair will be 3. So number of poles divided by 2. Okay. And this is the fundamental pole pair, because higher order harmonics will have we'll see higher number of pole pairs. So that is the idea. And omega is the angular frequency or frequency expressing radians, not in hertz. So 2 pi times that. And this is the supply frequency. Okay. And what is phi? So if you recollect the 2 circles that I have been drawing since morning, phi is the angular frame of reference on the stator side. So this is phi, is the stator reference frame. In stator reference frame, an angular measure. I will also introduce an expression where phi dash is the angular measure in the rotor reference frame, and omega r is the frequency associated with rotational motion on the rotor side. Okay. So what is omega r? Slip is defined as, in an induction motor, omega minus omega over omega. So omega r is 1 minus slip into omega. So this is my expression for MMF due to 3-phase currents flowing in a 3-phase distributed winding. So I have just written it. Actually, you can derive it by drawing the winding distribution, substituting current, and doing ampere turns, like current times winding. And if you do the mathematics, you will get this concise form. That's right. I have just given you, because we are only starting from MMF. Then we have to model permeance, then we will go from it. Okay. So this is the first thing. The next thing is have to model air gap. So this is our mixed eccentricity problem, right? So we are going to look at that. Thankfully, we are not going to model it all today because we have published literature available, so we can use that expression. But what I am going to do is, I am going to show what happens when you have uniform air gap, how you can model it, and when you have some kind of fault, how you can model it. So it goes step by step. Okay. So first, let us consider. So our goal is we have to come up with a mathematical expression for permeance per unit area, or at least permeance. So I need to come up with a mathematical expression for permeance, so that I can multiply my MMF equation with the permeance equation and try to synthesize the frequency components in the flux density. Okay? So that's the goal. Okay? So you will understand when you complete this exercise. So let us begin by assuming a healthy machine. So for a healthy machine, let the uniform gap between stator and rotor be G. Uniform gap between stator and rotor. What would be the permeance then? Permeance or specific permeance doesn't really matter to us right now, is a function of inverse air gap. So, right, it will depend upon permeance, will depend upon 1 over G. And since we are considering uniform gap, the gap is constant. It is irrespective of the position in the space in stator frame of reference, gap is constant. So P of phi is a constant which is given by 1 over the uniform gap between stator and rotor. Is this clear? I mean, if you are unsure, if you are unclear, please stop and ask. Don't hesitate. So I can easily represent this as, I am going to call this as a constant P naught. And the unit of this will be 1 over meters, right? It's the inverse of the gap. Gap is measured in meters, so 1 over meter will be the unit of this. And if you are looking at specific permeance, then you have to of course divide by area and get its unit accordingly. So this is P naught. So what is MMF specific permeance analysis say? If this is the expression for P naught, and the previous slide gave the expression for MMF, right? So MMF specific permeance says that I need to multiply my MMF with permeance. So let us do that. So MMF times permeance, which would be a flux or flux density, depends upon whether you are considering the area or not. And we are looking at stator reference frame, right? So from stator's reference frame, this would be nothing but P naught into the MMF equation itself. P naught is a constant. So instead of writing the summation, I am just leaving it out. You have to keep that in mind that the summation always exists. So there is a constant the stator frame of reference cos NP phi plus or minus omega. So MMF into permeance, that's all I have mathematically. And of course this can will change depending upon the order of harmonic you are considering. Now this is a flux from stator reference frame. I can consider the same flux from rotor reference frame. So to represent the same flux from rotor reference frame, I need to replace my angle from the rotor reference frame perspective. So what I will have to do is I will replace phi dash plus theta r or omega t plus or minus omega t. Right? So from the rotor reference frame, I have replaced my phi with the equation phi dash plus omega r. Np phi dash plus np omega rt plus or minus omega t. So once this flux or flux density exists in the air gap, we are looking at this flux density from rotor reference frame. This is how mathematically we are representing it. This flux density will have a frequency and it's a function of time, right? So that means the flux density or flux is time changing in nature. Now imagine an induction motor, there are rotor bars. The rotor bars are exposed to this time changing flux. Any conductor that is linked to time changing flux and EMF will be induced, and because rotor bars of an induction motor are short circuited due to end rings, the EMF will result in current flowing in the rotor, right? So whenever current flows through a conductor, there is ampere and there is turn, therefore it's ampere turn. That means another MMF is being produced due to current in the rotor. So due to current in the rotor, another MMF is produced. Say and that current might be lagging this flux by some angle, right? Typically lagging or leading. It will be at a different angle. It may not be in phase. Even if it has to be in phase, let it be. We can indicate it by introducing an angular measure. I am introducing an arbitrary angle to say that the current flowing can be at any angle with respect to the flux that induced it. It need not be in phase with that flux. That's all I am doing. Now this MMF, if you look at it from the stator reference frame, how will it look like mathematically? So we have to again replace this using the angle associated with stator frame of reference. So the MMF, due to current flowing in the rotor windings, can be so basically this MMF will interact with the air gap. The MMF interacts with the permeance, right? Permeance. So this MMF into permeance. So another flux will be introduced in the air gap due to this MMF FR. So this MMF, due to current flowing in the rotor, interacts with the air gap and produces another flux in the air gap, which is nothing but MMF times permeance. That is given by this expression. So it's a two-way process. You start from stator MMF produces flux induces current in the rotor. Once current flows in the rotor, it produces its own MMF. This MMF interacts with the air gap and produces a flux density. And that flux density is what we have written. Or flux is what I have written. Now I can look at this flux from stator frame of reference. Right? So this is the air gap flux due to current flowing in the rotor. This I can look at it from the stator frame of reference. So if I reconvert this variable into stator frame of reference, it will become NP into phi plus or minus omega t minus theta. So this is how the equation will look like. Am I correct? So this is in the stator frame of reference. So do you understand the flow? You start from stator, multiply with the permeance function, get the flux density, introduce the currents in the rotor, then rotor MMF will again interact with the same air gap, will introduce its own flux components, and that when looked at from stator reference frame will be like this. Now this flux density is also time changing in nature, can induce currents in the stator windings. It can induce currents in the stator windings provided the condition for this flux to induce currents in the stator winding is the pole pair numbers. So basically the number here, NP, or this pole pair number has to match with the main pole pair number. So the main stator MMF pole pair number and the air gap flux densities pole pair number have to match. If they match, currents will be induced, and the frequency of such currents are given by this omega. And as per this equation, because the pole pairs match, right? NP is same as NP in the other equation, right? Currents will be induced, and what will be the induced currents? The frequency will be omega, which is nothing but supply frequency. So that means whatever was the supply frequency, the same current is what we expect. And because of the space harmonic, we will see first, fifth, seventh like that. Okay. So this is the basic idea of the uniform air gap machine. The approach is the approach clear? So you start from stator MMF, model air gap or permeance, multiply them to get flux in the air gap. That flux will induce currents in the rotor, which will produce rotor MMF. The rotor MMF will again interact with the air gap permeance, produce flux. This flux can induce currents in the stator provided pole pairs of the flux in the air gap and the MMF of the stator winding match.
So then count the different frequency as a harmonics, because we have seen now whatever the purpose we have taken, that is appearing in different frequencies.
Exactly.
But here we are relating to the supply frequency.
So this is under healthy condition. So
Okay,
under,
first assumption you made is.
so this is under normal condition. So under normal condition, we expect only supply frequency. That's all we are saying. Now we have to go for a faulty condition. Right? So our first goal is, let us consider one fault. Let's say static eccentric fault. To keep things simple, I will take some measures, numbers. Rather than generalizing, I will give some numbers. Let us say the machine has a uniform, initially when it was healthy, has a gap under healthy condition. Okay? Under healthy condition, gap is 10 mm. 10 mm, you know, by now is quite large for an electric vehicle motor, but for the sake of ease of mathematics, we are using 10 mm. Okay. Whenever there is a static eccentricity, what is happening? The center of stator is offset from the center of rotation, right? That is the basic definition of static eccentricity. We have an oval stator. The rotor is rotating about its own axis. And the distance by which the minimum air gap happens. So, static eccentricity results in minimum gap of 5 mm. So what do I mean by that? So this distance is 5 mm. Initially the distance was 10 mm. Now the stator's center has got offset in such a way that the distance has reduced on one side to be 5 mm. So what would be the distance on the other end? 10 plus 5, right? 15 mm. So the minimum gap has now become 5 mm. Meters or millimeters, say. Healthy condition. Healthy condition was flat 10 mm. Right? Is everybody knowing? Healthy condition is straight line. 10 mm. When I have 5 mm minimum distance and a static eccentric fault, how will be my air gap variation along the angle? So the minimum will be 5 mm, maximum will be 15. Plot it. So this is 90, 180, 270, 360 degrees. Do you agree? This is the gap under faulty condition, under static eccentricity. I am going to call that as SP, static eccentricity. So we are just one step away from you starting to work. So what I am going to do is, I am going to write a mathematical expression and I am asking you to verify whether you get this function. Okay. So I am going to say, the literature published says, static eccentricity fault can be mathematically represented with the gap under static eccentricity. The gap under static eccentricity is gap under healthy condition minus the minimum gap times cosine of the angular frame of reference phi from stator frame. Angle phi from stator frame of reference. So this is the mathematical expression. So let me write it on the next slide just for clarity. So published work states that healthy minus the phi is the angle from the stator frame of reference. Okay. So I am going to give you a few minutes. I want you to check whether this mathematical equation actually corresponds to the function that we have drawn. So I am going to give you a few minutes. Check that. This is your time. You have 2 minutes time. Let's say I have given an expression. You know what is the gap under healthy condition, which is 10 mm. The minimum gap is 5 mm. Try to substitute different angles and see if you are getting what you want, which is this function. lab is a better place because you can put your notebook somewhere and write. Seminar have note tables. Anybody could verify? So did you substitute different angles for phi and check? So GH is 10 mm, G min is 5 mm. So if we extrapolate the phi versus G static eccentricity, when phi in degree is 0, what is cos 0? 1. So 10 minus 5 into 1, which is 5, will give me 5 mm. What is 90 degree value? 10 mm, right? 180 degree will be 15. 270 will be 10 mm. 360 same as 0. So essentially this mathematical expression given in literature is validated. So we can be safe. We can be confident that yes, whatever we say is correct. So this is the mathematical expression for this function Airgap under static eccentricity versus angle in degrees. 15, this is 5. So for our analysis, we don't need expression for Airgap or gap. What we need is permeance. And we know that permeance depends upon inverse of Airgap. Right? So permeance under static eccentricity will be 1 over, or depends upon 1 over gap under static eccentricity. So that is 1 over G healthy minus G min into cos phi. Right? Now let us look at from a practical perspective. Rather than writing like this, what I am going to do is I am going to divide the denominator by GH completely, the healthy air gap. So I am going to say that this function is same as 1 over 1 minus G min over GH times cos phi. Do you all agree? What is the, okay, now let us look at boundary conditions. When there is no static eccentricity, what is the value of G min? When there is no static eccentricity, what is the minimum air gap you can have? So this G min is the point, right? So when there is no static eccentricity, then G min vanishes. Right? So that means this becomes 0. If this is 0, then only we can say that there is no eccentricity for it. Right? So under healthy condition, G min is 0. The worst case, what is the maximum value G min can take? How far can the center be offset? The worst case value for G min would be GH, same as GH. So I can say that G min theoretically should lie between this distance, right? So what I can conclude is this ratio G min over GH should lie between 0 and 1. I am going to call this ratio as severity of static eccentricity. You can express it in percentage. So in the example values I have chosen, when we have 5 mm minimum gap for a 10 mm uniform gap machine, the severity is 50%. 50% is very high. When the severity percentage is less than 10, it's very small. When it is above 10, we are entering faulty condition and we have to diagnose it. 50% is huge, that we have to immediately stop the motor and diagnose it, fix it. Okay. So this expression becomes 1 over 1 minus severity of static eccentricity cost. So this is the expression for our permeance function, right? This is the expression for our permeance function. Now what I am going to do is I am going to let you substitute different values of angle. You know ES in this example is 0.5. Severity is 50%. Substitute different values of phi and create a table for different values of phi. What is the permeance function? So at 0 degree, what is the permeance function value? Sorry?
I think the formula is wrong. So instead of G and we should not be G and it won't work. Instead of G and we should be distance between the centers. Can you go?
Okay. So G can also be considered as the distance between the centers.
We should be distance between the centers. I mean, if you take instead of 5 mm, if you take 3 mm as G and the distance between the centers will be 2 mm. It will come 10 minutes to cos, like not 10 minutes to cos.
So if I, so you are saying that it should not be G min, but
It should be distance.
distance between the centers to for this. Probably I choose a wrong value of 5 because it's symmetrical, it is feedback. So you are essentially saying that if the centers C1 and C2 are offset by some distance, it makes sense. So that is G min. We can consider that as the G min here. But that's the distance between centers. Thank you for saying that. The same center initially, and then in the second case, the center of one circle is offset by a distance. Okay, so please substitute and tell me the values, please. One, 180 degree, 0.67, 270 degree, 1, right? So is everyone on the same slide right now? So what I am going to do is I am going to plot this function. angle in degrees.
Hello.
Versus fermions. So it starts at 2, goes down to 1. Check.
I feel like I'm piloting. Anyways, thank you. So the angle when it is 0, I have a peak value, and when it is at 180 degree, I have a minimum value at 360 degrees, going back to the original. The reason why I'm not bothered about the values at this point is I just wanted to look at the function and tell me what mathematical function it resembles. Sine, cosine function, right? It's a shifted cosine. So what I can say is I can generalize my static eccentricity air gap as a constant air gap, a constant P0 plus some P1 times cosine of phi. So this is how we will have to synthesize the permeance expressions for different fault conditions. Okay, is this clear? So this is how we have to model the permeance expression for different fault conditions. So static eccentricity in isolation is not useful. The most common form is mixed eccentricity. I am not going to go into the details, but based on literature we know that the mixed eccentricity permeance function can be approximated to this general form P1 cos phi plus P2 cos phi minus theta r, where theta r is omega r t. Theta r is omega r t, and phi dash is phi minus theta r. So this is from literature. I am just taking the expression and I am giving you. You are welcome to read a few papers and actually mathematically derive this for dynamic eccentricity and combine it for mixed and see what happens. So what I am trying to say is, so the mixed eccentricity air gap, its inverse when we model, which will give us the permeance, will be of this general form, or can be approximated to this general form. Why did we do all these things? Because we are interested in doing what is known as an MMF permeance analysis. Right? MMF permeance analysis demands an expression for permeance function. Therefore, we have to come up with this expression. So once we have got this, my MMF in the stator winding is MNS cos NP phi plus or minus omega t. Right? Do you all agree? This is the expression I wrote or I showed on slide. So what I am going to do is I am going to make mathematical multiplication, MMF times permeance. For the sake of time constraints, we won't do the entire multiplication because that will lead to too many terms and too long an activity. What I want you to do as a first step is just consider P1 cos phi, the static eccentricity component of permeance function, multiply it with this. So let us try to do it together. So the flux produced in the air gap due to the MMF interacting with only the static eccentric component of the permeance function. Again, this is in stator reference frame. So that will be minus P1 cos NP phi plus or minus omega t cos phi. What is the function cos A cos B? Trigonometric identity. Anybody remembers? Cos A cos B cos A.
2 into cos of A plus B.
Cos A plus B by 2.
Cos A minus B plus cos A by 2.
Okay, so we have cos A cos B as cos of A plus B by 2
Cos of A
plus cos of A minus B by 2, right? So we have two terms for this product. So the flux produced in the air gap due to MMF interacting with only the static eccentricity permeance function, we will have two terms. So let us, I'll give you a moment. So try to solve for that and write me the expression. So let us get the expression. That will be MNS P1 by 2 cos, the 5 terms get added, NP plus 1 5 plus or minus omega t, this will be one term, plus MNS P1 by 2 cos NP minus 1 5 plus or minus omega t. Is this okay? So I have cos A cos B. So the 5 terms will get added and subtracted. NP plus 1 5 and NP minus 1 5. There will be 2 terms. So this is all from the stator frame of reference, right? So we have to now look at the same flux density from rotor frame of reference. So the same flux density from rotor frame of reference would be NP plus 1 phi is phi dash plus omega t plus or minus omega t plus P1 by 2 cos NP minus 1 phi dash minus phi dash plus omega t plus or minus omega t. So the same flux density, when we look at it from the rotor frame of reference, will be represented like this. Any questions at this point? We haven't done anything extraordinary. We are just multiplying the permeance, one component of the permeance function with MMF. We are expressing it mathematically. So this flux density will interact with the rotor conductors, will induce current in the rotor bar. Once current flows in the rotor bar, there is a rotor MMF. That rotor MMF will again interact with air gap flux density, right? So when the rotor MMF is interacting, just for the sake of interest or interesting sake, let us assume that it is, I think I missed cosine function here, sorry. P2 cos phi minus theta. Please fix this, that must be a cosine function. It's not P2 into phi minus theta, P2 cos phi minus theta. This is corresponding to dynamic eccentricity, this is corresponding to static eccentricity. This is L02. Okay, there will be 3 terms, one corresponding to static, one corresponding to dynamic, one corresponding to L02. So what I am going to say is, this MMF, when interacting with the air gap permeance again it has to interact with the entire function, but for the sake of time and for interest's sake, let us assume that we are looking at the interaction between the dynamic eccentricity component and the air gap flux density. Okay. So let us multiply this permeance function with the MMF associated with the rotor flux density. Okay. So this is, let's just say phi rotor 1. So I have to take this and then multiply it with phi minus theta r. What is phi minus theta r? It's phi dash, right? So I can say that minus p1 by 2 cos np plus 1 phi dash plus omega t plus or minus omega t plus multiplied with p2 cos phi dash. This is the dynamic eccentric term, right? p2 cos phi dash. Is that okay? So likewise I will have another term mns p1 by 2 cos np minus 1 phi dash plus omega t plus or minus omega t into p2 cos phi dash. Right? So each term will result in two terms because they are product form. So when you expand it, you will get two terms. So we will essentially get four components. Let us consider just the first one for the sake of analysis in this workshop and let us explore it. I hope everybody is able to follow so far. We are doing the same approach as we did for healthy condition. Now that we have considered a mixed eccentric condition and we are picking and choosing like certain functions, you can do the entire analysis and you will get the same thing, but this is an easy way to check. Okay. So let us consider the first term. So let us just consider this one and let's see what happens. So if I multiply them, it's cos A cos B. So cos of A plus B by 2 plus cos of A minus B by 2. So what I will have is minus P1 P2 by 4 cos NP plus 1 phi dash plus phi dash plus NP plus 1 omega t plus or minus omega. So I hope you are able to get this. So NP plus 1 phi dash plus phi dash. Do you agree? So multiplying this term, so NP plus 1 phi dash plus phi dash, NP plus 1 into omega plus or minus omega t. So this is cos of A plus B by 2 plus I will have minus P1 P2 by 4 cos A minus B. So NP plus 1 phi dash minus phi dash plus NP plus 1 omega t plus or minus omega t. So I can simplify these two expressions. So I am just focusing on these two. So I am simplifying these two expressions. So this will result in NP plus 2 phi dash, whereas this will result in NP phi dash. Okay? Any questions? So let us now rewrite this expression after simplification. So after simplification, this will be m minus p1 p2 by 4 cos np plus 2 phi dash plus np plus 1 or minus omega t. So these are all flux components from rotor frame of reference, right? Because we are looking at angle phi dash. The same flux, if we look at it from stator frame of reference, this expression can be rewritten in this form. So in stator frame of reference, mns p1 p2 by 4 cos np plus 2 phi dash is phi minus omega t plus np plus 1 omega t plus or minus omega t plus mns p1 p2 by 4 cos np into phi minus omega t plus np plus 1 omega t plus or minus omega t. In case you have any questions, doubts, do not hesitate to ask. So let us simplify this. So I have omega t term here as well as here. I have omega t term here as well as here. So np plus 2 times phi minus np plus 2 times omega t plus np plus 1 omega t. So what will that result in? Minus omega t. Right? Do you agree? So this entire term can be rewritten like this: np plus 2 times phi minus omega t. If you simplify, np plus 2 into phi, np plus 2 into minus omega t, and then here I have np plus 1 into omega t. So np omega t will cancel each other. Minus 2 omega t plus 1 omega t will become minus omega t. Likewise, I can simplify the lower term, and this will be np phi minus or plus omega t. So we never thought life would get this complicated when we started. But this is only a small part of that long expression, right? So your homework, you know already what your homework is today.
So this is the omega t, right?
Omega RT. No, no. This is the numerator, this is the first term, this is another term. So let me rewrite this on next slide using simplified form. So my flux in the stator reference frame would be mns p1 p2 by 4 cos np plus 2 phi minus omega t plus or minus omega t plus mns p1 p2 by 4 cos np phi minus plus omega t plus or minus omega t. Right? So this flux in the air gap can induce currents in the stator windings provided the pole pair numbers of this function matches with that of pole pair number of the original stator MMF. What is the original stator MMF? We have to go back quite a few slides to even know where we started dropping mistakes on that. So here is the original pole pair number. NP is the original pole pair number. In this term I have NP plus 2. Can they match? What do we mean by that? N is equal to 1, 5, 7, 11, 13, like that. P is equal to pole pair, right? So if the 4-pole machine, P will be 2. Right? So NP would be a product of these two. So for any given machine, P cannot continuously change, it is one value. So P times N is a product. Right? NP plus 2 means, so let's consider N is equal to 1, it will be 2 plus 2, 4. N is equal to 5, it will be 10 plus 2, 12. In the original function, we had just NP. So can NP plus 2 ever be equal to NP? In this case, you have to check. Okay. So for example, what I am trying to say is, you can take a higher order NP from the MMF function and you can compare with NP plus 2. So if the orders match somehow, then currents can be induced. If the pole pair numbers never match, then current cannot be induced. So what you will realize is this term will not induce any current. But you look at the other term, this matches. So current can be induced. So what will be the order of frequency? It is omega t plus or minus omega t is there. Omega r plus or minus omega times t. Right? So there is an additional frequency component that corresponds to rotor frequency that is showing up in the line current due to mixed eccentricity fault. So this is the analysis you will carry out for different faults, and remember that we have just taken one term initially in one direction and one term in the other direction. When we went from stator to rotor, we started with static eccentricity Tomius function only, and we went back from rotor to stator, we just chose dynamic eccentricity function only. If you use all of them, you can see what is the impact. Invariably, you will see based on literature, what we know is we will have omega plus omega r and omega minus omega r, where omega is supply frequency and omega r are the rotor frequency. So sideband. So we will say, we call this as sideband elements. Sideband frequencies or sideband. So just about the fundamental. So if this is the 60 Hz or 50 Hz component, so this is 50 Hz, you will see one here, another one here, another one here. So these are sideband components. Okay? Sideband means something close to the fundamental frequency. So mixed eccentricity fault in motor current signature analysis is typically diagnosed by looking for this plus and minus omega r terms around the fundamental frequency or the sideband frequencies. So the moral or the summary of this long exercise is, if we have to carry out current signature analysis to diagnose mixed eccentricity, we have to do the spectrum or current spectrum or frequency spectrum and look for around the 50 Hz of fundamental frequency. We have to look for sideband components. So depending upon the rotor speed, it will be offset. Okay. So that is how you can estimate. So this is all fine for an induction motor, right? We started with uniform air-gap machine and everything. Now what is happening with electric vehicles is, the machine is inherently in some portion there is a longer gap. In some other portion there is shorter gap. So all this exercise that we did are considering the air gap is uniform under healthy condition. When we have to accommodate saliency, modeling becomes more challenging. So if you have a square gap under healthy condition rather than a steady line, so this square waveform indicates a salient port structures air gap under normal conditions without any fault. So that will, if you look at it from three-dimensional perspective, stator angle, rotor angle, this is how it will look like. So when you do the eccentric fault, the air gap can be thought of as a function of stator angle or rotor angle. It will be very different. So we have to come up with an inverse function. An inverse function using traditional approaches have some drawback when it comes to modeling a salient pole machine, which is quite common in electric vehicles. So the traditional way of modeling inverse air gap has found to be inadequate, and we had to come up with a newer method of modeling this inverse air gap. And this newer method of modeling gives us the inverse air gap function and a mixed eccentricity fault to be a function like this. Some constant times cos L5 plus or minus m theta r, where L is a number that varies from 0 to infinity, m is a number that varies from 0 to infinity. So it's an extensive harmonic order. So you have to approximate it at some point, right? So essentially that's the idea. Okay. So you will see that this is how we have to take inverse air gap function, and then we have to carry out MMF specific permeance analysis, and when we do it for salient rotor structures, different fault frequencies are
We have a breaks.
and finishing. So this can be visualized. So healthy condition results in certain frequencies, static, dynamic, mixed.
So, what is the G actually? The C set is that
Healthy. I just for consistency, I do HE rather than H. HE means healthy. Okay. So we can see the frequency spectrum like that. So this is how we have to theoretically expect what fault would introduce what components. So this, let us stop here, and then after a break we will come back and get started with the software. Thank you.
Quite easy. In fact, modeling is a big research domain. If anybody is interested in condition monitoring, you should consider modeling as your one of your areas. So just creating real-time models. So if you have access to a real-time simulator, creating a real-time model of a motor which can accommodate such fault and run in real time it will get you at least one PhD, if not more. There are lots of opportunities. So what is coupled circuit model? It's a very simple standard structure. You have your stator voltages, 3-phase voltages or 99 voltages. Typically these are all phase voltages. You have stator resistance, 3-phase, and this is going to be a matrix. And then stator phase currents plus the rate of change of flux linkages associated with stator. Right? And lambda is nothing but LSS-IS plus LSR-IR, where LS is the self-inductance matrix and LSR is the mutual inductance matrix. And you have a 3-phase system, you have LAB, LAC, LBC like that. Right? And for the rotor circuit, because we are looking at induction motor, we can model the rotor bar as a circuit. Okay. So
you have a permanent magnet machine, then you have to imagine there is a fictitious winding. Okay, so then we can model it that. So these are the voltage expressions. The torque acting on the motor shaft is given by load torque plus inertia component, like acceleration or deceleration torque. And we can use co-energy, rate of change of co-energy for computing torque. So it's d by d theta or dou by dou theta of 1/2. Usually half Li square typically is what we will use, but because this is matrix, we will have to use appropriate dimensions. That's why we have IS transpose LSS IS plus IR transpose LR IR plus mutual inductance series. Okay. So these equations themselves are very standard. Whether you want to model motor for eccentricity or normal conditions, these are standard equations. But what really happens is when we have air gap non-uniformity, if you recollect your morning session, we wrote expression for inductances, right? Inductance is n square over reluctance. Reluctance depends upon air gap. Now air gap is no longer a constant. That means your inductance will no longer be a constant. Inductance will be a function of theta. So in this expression, torque expression, each of the terms, inductances are functions of theta. So as rotor position changes, the inductances of each of the windings at different rotor positions are varying. Okay. So calculating these inductances is one of the most time-consuming job in this approach. And in order to calculate inductance, a specific type of approach is reported in literature. It's called as modified winding function approach. It's a very advanced topic. We are not bothered about it. The main reason is the other approach of modeling, which is finite element based, is much simpler when it comes to modeling. So we are not too bothered about modified winding function approach. So I won't go into the details. I want you to be aware that it is possible to model inductances which are function of rotor position using the reported technique in literature called as winding function approach or modified winding function approach. The idea is very simple. If you consider a stator as shown here with just two conductors, as you go around the stator in one direction, let's say in counterclockwise direction, the turns function includes the total number of turns. Okay, so if you have a conductor arrangement like this, if current is flowing inside or into the page on this conductor, then it has to come out of the page on this conductor, right? So the direction of current vector is also taken into account in sketching the turns function. So what I'm trying to say is, as you go in here, it's like using Ampere's law. So the net Ampere turns enclosed in this path would be, if n number of conductors are here, then it will become plus n at this position. As you go around, you have to, because the direction of current has reversed, you have to subtract. So it will become minus n, plus n minus n becomes 0. So this type of drawing, where you sketch the winding distribution and the conductors and the current flowing through it, using the direction of current flowing through it, is called as turns function. Okay? And then the winding function would be subtracting the turns function. So this is for a three-phase stator, which has multiple slots and multiple conductors. So you can sketch the three-phase turns function. Okay? And then you can calculate inductance using this expression, where NA and B are the turns function, G inverse is the air gap inverse function, and these are average values of the turns function. So this is again a sophisticated approach. We won't bother about it too much at this point. I want you to be aware that there is a mathematical technique called as modified winding function approach that will allow you to compute inductances that are rotor position dependent. Okay? And you can see the inductances for different faults. So under healthy condition, the inductance is given here. Under static eccentricity condition, the inductance changes.
and a particular rotor bar. As you rotate, the rotor will be of this shape under healthy condition. When you have a static eccentricity, the inductance itself will change like this for one rotation. So phase A to a particular rotor bar. For dynamic eccentric condition, the inductance will be same in shape as static eccentricity, but the magnitudes will be altered. And for mixed eccentricity condition, it will be a combination of static and dynamic, right? So it's going to be something like this. So this is how you will synthesize inductance. And these are the stator self-inductances, or basically LAA, LAB, LPC. So basically, these are mutual inductances of the stator windings, LAB, LAC, and LBC. And a healthy condition and a mixed eccentric condition. So they are completely position dependent. So you can use them to simulate. But this approach is very sophisticated, mathematically intensive, and therefore it's not as popular now as it was a few years ago. So now the most popular technique is what is called as finite element simulation. So in this lab, you will have access to a particular software. So this is a commercial software. You may or may not have access to this from your institution. If you don't have, you can look for some free software tools that may give you similar capabilities. Okay. But commercial software will come with its own advantage. So what I am going to show you is quickly how you can model a motor, let's say, and then you can go into modeling eccentricity fault, right? So if you open a commercial tool like this is called as ANSYS, and the software is electronics desktop. We are using a student version for the purposes of this workshop, but you can buy a license. So the easiest thing is to open an example. This software is very powerful. You can do lots of simulation with it, lots of different types of simulations with it. I am not going to talk about the software, that is not my intention. I am just going to focus on how easy it would be to model a machine. So let us open an example, and since we have been talking about induction motors, let's get started with the induction motor. When you click on open examples, it will give different types of tools within the software. We will go into what is called as an RMXPRT tool. It's a library basically, it allows you to quickly model motors. This has multiple examples. I am going to take induction motor IND-M3, let's say, just a random. And I am just choosing YZ206 as an example. You can choose any example, I am just choosing one example. The first thing I will do is I will save this because it's an example file. I don't want to corrupt it, so I will save this on the desktop. Okay, I have saved it on my desktop, so it's a copy of my example file. So you see here this example file has stator, rotor, everything. So you can easily expand it, and you can go double click on the machine, and it says 3-phase induction motor, 6-pole machine. These are the details that are given by default. And if you expand this machine, it says there is stator, there is rotor and shaft. So stator, if I double click, it says this is my outer diameter, this is my inner diameter, this is my length of the shaft, the length of my stator, etc. Stacking factor, steel type, number of slots, slot type, so many details are there. So the good thing about this library is I can edit and see what happens. For example, right now there are 72 slots. It's a 6-pole machine. Typically, number of slots per pole should be an integral number. So 72 should be a multiple of 6. Let us choose another multiple of 6. Rather than 72, let's say I use 36. Okay. So I will give 36 slots. If I give OK, you see already it visually updates. So then it becomes easy for you to play around with it. Sorry. Play around with it. So you can go back. Now you may diameter. That means the core will get saturated probably with this. change around a little bit, but you don't have to bother too much. If you expand stator, there is slot specific information you can enter. For the selected slot type, what are the dimensions? The winding type, is it single layer or double layer? Number of conductors per slot? Number of strands in each conductor? What is the wire size in diameter? So all those details you can give. Again, if you don't know many of these, you can leave them to default and you can work with it. Okay. Rotor, if you double click, it says number of slots is 58. Outer diameter of the rotor is 209.2 mm. So if you recollect the default value of inner diameter of stator, it was 210. So the difference between the two will give you air gap, which is like less than 1 mm, right? 0.8 mm. So the concentric gap would be just difference in the diameters. It will not be difference by 2, it just will be the difference. So if you just draw two circles, the difference in the diameters will give you the gap. Length will be fixed. In the diameter is almost. In the student version, there is a bug. So if you go into rotor window and if you click on the material type of the steel, the software will crash. So don't do that. It's just a bug in the student version of this 2024 release.
Latest is 2024 release.
Just in 2024 release they have this bug. So when they release the next version, they will fix it. I mean, the reason why I'm saying that is otherwise people have built it from scratch, but anyways. So likewise you can change the slot and winding for the rotor too. And in the induction motor, the winding is like there's just a cage, right? So you can decide the cage, aluminum type, number of, like what is the height of the tail ring, what is the width, what is the ending conductor, etc. And then shaft diameter you can specify whether you want to have a magnetic shaft or a non-magnetic shaft can also be selected. So usually you will not have a magnetic shaft, you will just have stray flux along that. And then you can go into the analysis and you can set up, you can say what is the rated output power, what is the rated voltage, rated speed, rated operating temperature. And you can enter these details. These are available from main rate. So you should know them for any mode. And then what you will do is, you will click, right click, and you will say analyze. And you will do some analysis, it will give you a message. So until now, there is nothing fun. So you are using a model, and you can enter parameters, you can change the dimensions, but after this comes the biggest advantage. So what we really want to do in our analysis is, we want to have a setup where we have a motor model which can be excited from an AC source or an inverter. The motor must spin connected to a load and the current calculated at different instants must be available to us as a measured data. Right? That's the goal of our, because we want to do motor current signature analysis. Right? So we want to run the motor excited from a supply. When if the motor is loaded, it will draw current. I am interested in that current waveform, time domain current waveform. Right? That is the goal. In order to carry out such a simulation, this software has what is known as transient simulation tool. And the good thing is, if you have a full version, you can carry out transient simulation easily. So by right clicking on the setup, once you have analyzed, you will get an option called Create Maxwell Design. And if I click on it, it will take me to analysis. 2D design is fine because we are looking for static and dynamic. If you want to do inclined eccentricity analysis, you remember inclined eccentricity is along the shaft, there is still tilt. Right? Then you have to generate 3D design. Now just looking nicety perspective and generating a 3D model and clicking OK. And then in a few minutes, modeling of your motor becomes very easy if you have some basic dimensions. You can use an example model, you can play around with it, you can change the gap, you can change the slots, you can change the conductor arrangement, and you can generate a model on which you can carry out transient analysis. When we do this step, when we go from RMXPRT model and say create Maxwell design, the default simulation that the software expects us to do is transient simulation, which is what we want to do. Basically, we want to run the model at different time instance and see what is the current, what is the magnetic flux density, etc. Because this is a 3D model, it generates a lot of, it takes some time, it takes a few minutes, and it is trying to generate different elements. If I had selected 2D design, it would have generated the model in 2D view, and it would be much quicker. The drawback of the student version is once we are in transient domain, we cannot do any simulation because we don't have the license in student version, but in full version we will have the license. So the default setting of this model, of this software is such that it will generate a full model first, and then it will analyze. If it is axis symmetric, then it will take only a section of the model and it will place. Because that is symmetric model, so it is just using 1.5. That is good enough to analyze. We don't need the complete model, is what I'm saying. So rather than this, what I am interested in is a complete model. So what I have to do is, rather than using the PV half part, I want to do a complete model. So to do a complete model, I need to go into the RMXPRT model, right click, and if I click on design settings, so this is an important part, and if you go into user defined data, enable it, and you type fractions is unity, and then if you reanalyze, and then you can basically create Maxwell design again. This time let's do 2D design so that it is quicker, and you will see that you will get the complete motor model. The example I chose was not a good one. So it is able to generate 3D model because of the basic dimensions. I changed some values, right? So it's probably made some mistake. It's not a proper value. It's showing some error. So let's wait for one or 2 minutes. Once the model is completely generated, I will show you the transient mode, and then you are free to work on the model like software as you please. So running such simulation requires a high computing power system. Right? You cannot run it on a regular laptop.
It takes more time.
It will take some time. Yeah. It will run the
Sorry, where that is required.
RAM and memory. In general, a better processor. But usually the computers in your research lab will be sufficient. They are high performing computers by default.
Say if you are studying startup sequence, you set it to 0. If you are interested in steady state behavior, set it to a speed close to steady state because you can minimize the simulation time. Okay. What is the moment of inertia of the system along with the load? What is the damping constant? You can also give a load torque. It can be a constant value, or you can say until the particular speed the load torque is a particular value, and beyond that speed the load torque changes. Or you can also express load torque as a function of time. If time less than 0.2 second, load torque be 0, else load torque be full load, right? Whatever the value is. Then it will apply load accordingly. So you can do different things. So this is one important parameter. The other thing is excitations. So in excitation, you will have 3 phases. So phase A, you can select what type of excitation you want, whether you want to give current excitation or voltage excitation or an excitation from an external circuit. So if you want to have an inverter driven machine, you will set this to external excitation and you will have to model the inverter. Okay. But typically if you have just a voltage excitation, that is more traditional, and then you will give what is the resistance of the coil per phase resistance, and then you will define the supply voltage. So peak value of the supply voltage times sine 2 pi of t for phase A. For phase B, everything will remain same except there is a phase shift, and phase C another phase shift. Okay. So these are the 2 things that you will modify. Once that is done, you will go into analysis and you can right click or you can just open the setup and you can say how long you want to simulate for and at what time step you want to simulate the system. Right? So if you really want final time step, it's going to take longer time. If you want to simulate for longer duration, it will take longer time, almost 2 days. So if you are doing a simulation of a 50 Hz system, in order to get a good looking sine wave, you want at least 20 to 30 data points. Right? So 50 Hz in time domain would be 1 over 20 milliseconds. So you want to do at least 20 points. So 1 millisecond should be the minimum time step for 50 Hz. 2 milliseconds again 25 data points. So maybe 0.5 milliseconds or 1 millisecond will give you a good resolution. But then you are going to extend your simulation time. Right? So this is what. And the good thing is in this, you can also save magnetic field information at different instants in time. And you can create, you can say that save every 0.3 seconds or 0.2 seconds like that. Or you can create a table and you can say at different local positions to save the magnetic field. So that at the end of the simulation you can also visualize how magnetic field has changed. So with this approach you can model the machine quite easily. I will close this and open up a 2D model because I badly need a 2D model to show you how you can introduce eccentricity, right? So by definition, as Mithunandan pointed out, we are going to offset the centers and see. So that is what we really want. In fact, I can even look at it here. So just zoom in. This is a better view for me. So if I want to look at eccentricity, right? So it clear? 2.9 mm is the distance. So go on to measure, select the starting point, position, and then you go into that. So from one side rotor tooth to stator tooth, whatever is the distance is there. So 2.9 mm is the distance in the healthy case. So if you want to introduce 50% eccentricity, static eccentricity, you will select the stator. So if you want static eccentricity, you select the stator and offset it in one direction, opposite direction. If you want dynamic eccentricity, select the rotor and offset it by some distance in one direction. And if you want mixed eccentricity, you have to move both a little bit in one direction. Right? So that is how we will do it. And when you do that, because of the software setting, we may have to delete this moving circle first, move everything and redraw a moving block and do the simulation. Otherwise, you will see encounter an error in this software. But what I am trying to say here is, it wouldn't take you, to learn the software itself, it will take you some time. But once you have acquainted yourself with the software, there are so many video tutorials nowadays from the supplier. You can also find on YouTube there are different individuals doing tutorials. But once you have acquainted yourself with the software, modeling a motor and introducing eccentricity fault is going to be way easier than the other approach of modeling a motor using coupled circuits and introducing eccentricity fault mathematically. Okay. So that is the big benefit of finite element simulation. So the main idea of the workshop was to show you, but there is not much time left for the day. But what I want you all to acquaint with the software. So what I would recommend is, don't start with this all these things. When you want to get started, the best way is going to help Maxwell PDFs. Then there is Maxwell Getting Started Guide. What I would suggest is, start with something called as magnetostatic problem. Magnetostatic problem means you are going to give DC current into the coil and see how flux is going to be distributed in that environment. That is what we call as a magnetostatic problem. That is not a problem of interest to us, but that is the starting point in all your analysis. So magnetostatic analysis means giving DC current into the coil and then seeing how flux distribution occurs in the machine. Always start with that. Once you know how to build and run a magnetostatic example, go into transient analysis, Maxwell transient problem example. So don't start with transient problem, because that's not how you learn. Start with magnetostatic, do the first 1 or 2 examples, then go into transient problem and try to do the analysis. And just for your information, although I have shown example of only a motor, this software can also be used to model your high frequency power converters, especially your inductor, your transformer, or high frequency systems. You can carry out thermal analysis. You can also do loss analysis. So basically, you will have an advantage when it comes to research publications. So if you are doing DC-DC converter, you may not have a transformer, but you will still have an inductor. So you can do the inductive element as a part of this, carry out loss analysis and see what happens, and you can add it to your publication. That will be helpful. So it's a tool. I'm not talking about this specific vendor's tool. What I'm saying is, any finite element simulation tool is a very useful tool, because modern day industries are going towards what is called as creating a digital twin of hardware system. So they expect engineers to be able to work with hardware, software, and a mix of both tools. And these kind of tools are going to help you in that. So with that, I will leave. So what I recommend you is to get started with the Maxwell 2D may not be able to complete it today, but today is just a start. You don't have to worry about completing everything today. Give this a try, and if you have any questions, I'll be happy to answer. So I'll hang around at least until 5:30. Thank you. One of the analysis we are trying to do is taking these motors, we want to introduce eccentricity in these motors and see how they behave. So we are not creating the design, we are not designing the motors, right? We are using the correct design. We are just introducing a fault of our choice and we are seeing what is the impact on performance. Interestingly, we found some motors have a torque reduction due to eccentricity. So the performance may not always worsen. Cogging torque worsens, but sometimes torque will improves. We have to do more research. All I'm saying is these kind of designs are also possible. So if you really look at this model, so you see here phase A is all these highlighted sections of phase A. So this is a 6-pole machine. Phase B is here, phase C is here. And the excitation, these are all current excited. Like we chose to give current excitation, but ideally voltage excitation would make more sense. Current excitation means you are circulating a fixed value of current and you are seeing its performance. How much torque can it develop? Rather than loading the motor mechanically, we are injecting current and seeing what is the torque develop, what is the rate of itself. Okay. So that's the idea. So when these magnets, they are magnets, so you can actually you will see the magnet type from the library. So the magnetic properties can also be edited. So if you are using a magnetic material of your choice, you can edit its characteristic. You can introduce non-linearity or you can eliminate non-linearity and you can do simplified simulation. So there are many benefits to a finite element simulation. What I'm saying is you now have access to as close to real world as possible with this tool. Right? You have already access to a Chevrolet Bolt motor. Now you can excite it with the inverter in the software and see how it responds. You can introduce valves, you can load it with different driving cycle conditions and see what is its impact.